Okay, so what we're going to do tonight is revisit our introduction to derivatives. So we were looking at the fundamental concepts that underlie the concept of a derivative, and we started to look at this one example, and we'll start with this one and work our way through a few more before we actually introduce the rules of differentiation. Okay, so here you have this graph for the function f of x equals x squared, or y equals x squared, and you can see it's a parabola. And so here is the definition that we derived the other day. And what it says here is that the slope of a tangent line to the function at point A is actually the limit as x approaches A of f of x minus f of A over x minus A. So we use this definition to derive the slope of the function at the point x equals 3. And that in turn represents the derivative of the function when x equals 3. Okay, so how do we do this? So here I've repeated the definition. And so our particular case, remember f of x is x squared. And then 3 is a. I should have put that in here. A is 3. F of 3 is 9. Okay, so based on this definition, what we're looking for is in the numerator, f of x minus f of a. And of course, f of 3 is 9. So in the numerator, we have x squared minus 3 squared, or x squared minus 9. In the denominator, we have just x minus a, or x minus 3. So this is the limit that we need. Now, of course, there's just one little problem. The way it's written, you can see that this direct substitution would lead to division by 0. But we've seen already how to get around that problem. If we can come up with an equivalent function that does not have division by 0, we'll still be able to find our limit. So the strategy that we followed here was to factor the numerator. X squared minus 9 is rewritten as x plus 3 times x minus 3. And you can double check that with FOIL. And then in the denominator, we have x minus 3. So these two cancel each other out. And now direct substitution brings us to 6. Okay, and so 6, and yes, on the next slide, it reminds us that this is the form 0 over 0, which means that we can possibly algebraically manipulate that function so that we can find another expression that will give us the correct limit. And that's what we did. So anyway, the long and short of it is that for f of x equals x squared, when x equals 3, the slope of this line, this tangent line, is 6. Okay, so that means that the derivative of f of x at x equals 3 is 6. So think of the derivative as basically just the rate of change of y with respect to x. So you have to think about it this way. Imagine that x, we're starting at 3, x changes by an infinitesimal amount. What happens to y? That's what this is telling me. It means that whatever the infinitesimal change is in x, the change in y is 6 times that. So like imagine if it increases by 0.0000001 or something like that, then y will change by 6 times that. But only at this point. Now, if you notice very carefully, you look at this function, it's a curve. So that means if I define or put a tangent line at any other point, I'm going to get a very different result. In fact, right here, for example, if I have a tangent line at x equals 0, I'll actually wind up with a horizontal tangent line. So that means that the slope when x equals 0 is 0. Okay, so when you have a nonlinear function like this, x squared, that means that the derivative will depend on what value of x we're looking at. For a straight line, the slope is the same throughout, so the derivative never changes. And we'll see examples of that. But for any other type of function where there's some curvature involved, that means the derivative will be different at every value of x. Okay, now, you might remember we mentioned that there's actually two equivalent ways of coming up with a limit. Okay. This first approach that we've already used tells us that what we can do is what we just did, which is to say, well, why don't we take the limit as x approaches a of f of x minus f of a over x minus a. But equivalently, what we can do is take the following expression and take the limit as h goes to 0. Okay, so in other words, you have to imagine that we're at a point on this function. Let's say it's the same one. And here's 3, and here's the slope. All right, that didn't work out so well. Let me try it again. Oh, that's better. So the slope at this point is 3, 6 rather, sorry, it's 6. So h is really just an infinitesimal change. In other words, whatever a is, let's say it's 3, this h is an infinitesimally small change, which means we're moving from, let's say, 3 to 3.00001 or something like that. So in the numerator, we're looking at the difference between f of a plus h minus f of a. And then in the denominator, we have the actual infinitesimal change. What we're trying to do is take the limit as that goes to 0. Okay, so you see the difference here is that here we're trying to see what happens when x gets as close as possible to a. Here we're trying to find out what happens when that infinitesimal change is as close as possible to 0. Now this approach can be a little messy. So you'll see what I mean in a second. So remember the function is f of x equals x squared. So f of 3 is going to be 9, of course. But what about x, 3 plus h? Okay. So, oh, sorry, I wrote it incorrectly. This should have been a plus h. Actually, let's do this. I don't want to have to keep scrolling back and forth. I'm just going to copy this definition again. I'll sneak it down here. Okay. There's just about enough space for everything. All right. So in other words, there's the definition. So the a is 3. We know that. And we know that f of x is x squared. So f of a plus h is the same thing as f of 3 plus h. And f of a is just f of 3. And h is just whatever it is. This is usually the tricky part. What do we do with that? Well, and let me do this in the next slide. If f of x is x squared, a is 3, then f of a plus h equals f of 3 plus h, which equals 3 plus h squared. Okay. Now, because this is a binomial term, it has two terms, it's the sum of two terms. I can solve for this with FOIL. Okay. Oops, hold on one second. And so f is here, O is here, I is here, 3h again. And then finally, last would be these two terms, which is h squared. Okay, so all of this ultimately equals 9 plus 6h plus h squared. All right, so that being the case, we can plug that back in to our formula. Okay, so we just got through showing that f of 3 plus h squared is 9 plus 6h plus h squared. All right. And so that becomes, that's where this is coming from. That's better. All right, and then f of 3, we've just gotten through showing up here that it's just 9. Okay, so that's easy enough. So we're taking the limit of this expression as h goes to 0. All right, so let me just copy this onto the next slide. And so if you expand this up here, 9 plus 6h plus h squared minus 9, it reduces to 6h plus h squared. And so you've got the limit of 6h plus h squared over h, which of course reduces to 6 plus h. And because h is approaching 0, we ultimately end up with 6. So it has to work out the same as the other version of this limit derivative definition. They both mean the same thing, basically. So when you take this limit, you're going to end up with the same result. So that leads to the next result. The derivative of a function at a specific point, we can summarize this by writing the following. F prime, by the way, I want to mention here that one of the multiple ways there are to express a derivative, I might as well mention them now. There's at least 3 different ways of writing a derivative that all mean the same thing. The derivative of f of x can be written as f prime of x, it's called y prime of x. You also sometimes see it written as dy dx. Now, that dy dx, the reason why it's written that way is because the derivative itself, remember, is ultimately a slope. And normally a slope can be expressed as delta y over delta x. So what you have to imagine here is that as delta y approaches 0 and delta x approaches 0, the slope can be written as dx, a dy dx. So think of delta y as a small change in y, whereas dy is an infinitesimal change in y. The same thing, of course, is true for x. So that means that dy dx is essentially the limiting case of delta y over delta x. And so it's a frequent case that we'll be writing dy dx for our derivatives. The notation, is interchangeable, but sometimes one of these forms of writing the derivative is more convenient than the others. And so we'll try to use the one that seems to be the most convenient. You'll see what I mean as we go into more examples of this. But sometimes it's easiest to write dy dx, sometimes it's easiest to write f prime of x, and sometimes it's easiest to write y prime. It depends on what we're trying to do, but they all represent the same thing. So just remember, all 3 of those mean the same thing. Dy dx, f prime of x, and y prime. They're all equal to the derivative of f of x. Now, as far as the f prime notation goes, you can see one of the advantages right here. I can write f prime of a to remind me that I'm looking for the derivative at a specific point. So you can see I can't do that with dy dx or y prime. So if I need to know what it is at a particular point, then the easiest way to write this is f prime of a. Okay, so you'll use, typically we'll see them all used interchangeably, but sometimes one of them is more convenient than others. That being the case, you can see what this is all about. F prime of a simply means whatever the function is. And again, we might as well just keep using this one because it's simple. And we just proved using both approaches that the slope of this tangent line is at a equals 3 is the derivative of this function when x equals 3. They both give us the same results. Okay, so for example, this one. Well, we've already kind of done this, so we can get this done very quickly. So remember, f of x is x squared. We've chosen a to be 3. So we have x squared, f of x is x squared, f of a is 3 squared, which is 9. And then we've already seen that this has to be reduced. And that's it, we're done. All right. And the other method, and again, we've already seen this, but we'll do it one more time. Oh, actually, I don't want to put it here. I'll put this on the next slide. That's better. So you can remind yourselves what it looks like. Okay, so a is 3. F of x is, of course, x squared. So we have 3 plus h. F of 3 plus h squared minus 3 squared over h, which we've already seen reduces to this. And then, of course, this reduces even further to simply 6 plus h. So we end up with 6. All right, now every derivative could in principle be done this way, but except for very simple cases, this is going to be a major headache. So a large number of rules have been developed that let us calculate derivatives directly without ever invoking these definitions, with the understanding that this is what's going on behind the scenes. In other words, it's like anything else. You don't have to understand the internal combustion engine to drive a car. It was designed to make it easy for anyone to drive it. And something like that is happening with these rules. You don't have to know how these limits work in order to use the rules, but probably you shouldn't neglect it either. It's important to understand what the rules are doing. All right, so let's see. Oh, here we go. We've got another example. Now, here's f of x equals x squared plus 3. And now this time we're interested in finding out the derivative when x equals 2. Okay. So let's use the first approach. And remember, the function is, this time it's a little bit messier. It's x squared plus 3. And a this time is 2. So that means that f of a plus h will be a plus h squared plus 3. Remember, too, just as an aside here, if f of x is x squared plus 3, You're just literally replacing every x with a plus h. So that's where this is coming from. Over here, and that also implies that f of a, just plain f of a, would be a squared plus 3. Again, it's just direct substitution. So now it's just a question of plugging in the value of a, and then expanding, and then taking the limit. Okay. So let's see. I think I will copy this to the next slide. Again, so that we don't have to keep scrolling back and forth. If you notice, all that happened in this line is that all the a's are being replaced with a 2. Now they're expanded. So let's just quickly go to the next slide and show how these are being expanded. So for this first one, we have 2 plus h squared plus 3. So the 2 plus h squared can be solved with FOIL. Or 2h, 2h again, and h squared. And then, of course, at the end, you're just adding this 3 here. So you've got 4 plus 4h plus h squared plus 3. So you can consolidate all that. You can write it as h squared plus 4h plus 7. You notice how I've rewritten it. It's normal practice with polynomials like this to write them in descending order of the exponent and save the constant for last. It doesn't have to work that way, but it's common practice. It's just that's the way it's done. It's like once you establish a convention, it's pretty important to stick to it. It's like if you notice with lights, traffic lights, there's no reason why the red has to be on top. That's just how it's always been done. I mean, red always means stop any way you look at it. But imagine how many accidents you might cause if you actually tried to have a light where the red was on the bottom. That wouldn't work too well, would it? Well, this is a lot less serious than that, but it is still an important convention. Okay. Yeah, boy, that would be confusing. All right. Anyway, so then you've got the second term was a squared plus 3, which is, you can see that's going to be, we're subtracting off 4 plus 3. So ultimately, you end up with 4h plus h squared over h, and that nicely reduces to 4 plus h. And that just gives us 4. So that means the derivative of this function when x equals 2 is 4. Or think of it this way, the slope of this tangent line is 4. It'll be different at every other value of x. Or we can try this approach. But ultimately, what we will do is, for the most part, pick one or the others. This is the one that we'll be sticking with, this definition. It's just, there's a lot of reasons why this one is more convenient. We'll stick with this approach. Of the two, we'll find this one is probably the most convenient. And so f prime of x, the first derivative or the derivative of this function, is formally defined in the following way. So, I mean, ultimately what you're trying to find out is, here's your function. Now, as you keep getting closer and closer to, let's say h is 3, the tangent line slope will be different until we exactly hit this point. So we're trying to get as close as we can to that point and use that to define our tangent. Now, not all functions can be have a derivative, or at least not at every point. In other words, a function can be differentiable at some points and not at others. This one doesn't matter where you are, where you go, somewhere along the way, whatever point you're looking at, you can find a slope of a tangent line for this function. But what happens if you have something like this? And we've seen these already. This is y equals 1 over x. Can you find a slope? Or can we find a tangent line at x equals 0? No, because the function is not defined at that point. So what that means then is that the derivative, I'll call it f prime of 0, is undefined. It doesn't exist. Now, for any other value, like for 1, for example, no problem. I can find a tangent line right there. Okay, but for 0 itself, since 0, the vertical axis is an asymptote, the function is undefined. You recall that the domain does not include the 0. And that implies that the function can't have a derivative at x equals 0, but it will have one everywhere else. So we have to be careful. Not every function can be differentiated or have the derivative taken at every single point. So formally, a function is said to be differentiable at a point if a derivative exists at that point, which requires that it must be continuous at that point. And here's an interesting result. It must have a unique tangent at that point. And this is something we'll maybe not get to for a while. But let me show you another case where the derivative does not exist, and it's because of that second requirement. Imagine it's something like this. Whenever you have a sharp break, like a point like that, or sharp edge or curve, however you want to look at it, or something like this, the derivative is not going to be defined at that point because the slope is going to change quickly from one side to the next. And that's exactly what we don't want. So this one will be, let's say this is x equals 2. F prime of 2 is not defined. The only way to really describe this, I mean, we'll look at it more later on, but is with what we'll call a sharp break in the function. It's not a discontinuity, but you see how it just dramatically changes from one to the other, one side to the other of that point. And the same thing is true here. There's not going to be a derivative here either. And it's to do with the limits, by the way. Let me finish this and I'll show you a graph that I hope makes sense. Remember, the derivative is simply the slope of the tangent, which in itself is a limit. But if you recall the way limits work, in order for a limit to exist, let's say it was something like this. The limit as x approaches 3 from the left, let's say that it's L, and the limit as x approaches 3 from the right, they're both the same. And this implies that the limit exists. But when you have one of these weird cases with a sharp point like that, that's what the rub is. The limit from the left is not going to be the same. Okay, they're approaching from different sides. The limits will not be equal to each other. Let's put it that way. Okay, you see how this one is getting progressively closer to a positive value. This one is getting closer to a negative value. And so the limits, the one-sided limits, do not match each other. And so we don't have a derivative at that point because the two-sided limit is not defined. Okay, now we're not going to run into this very often. It's a very strange case. You need some very bizarre functions for this to happen. What you're more likely to run into is the case where there's a discontinuity of some kind. Okay, like here is a classic example, but you know, the cases that we had where there was a hole, something like that. There'll be no derivative at that point because the limit is undefined. Okay. So those are the strange situations where the derivative doesn't exist. All right, now let's use this definition to find the derivative of f of x equals x squared. So square root of x. Okay, so here's the formal definition. And since the function is simply radical x, that means that f of x plus h is just simply radical x plus h. F of x is simply radical x. So what do we do with this one? Well, one thing we can do whenever we have square roots like this, it can be a bit of a mess. And so we had this discussion the other day about conjugates. By the way, before you even do that, let's see what happens if we directly substitute. Well, we've seen this before, 0 over 0. So we need to find a way to rewrite this function in such a way that the limit is defined. If it's possible. I mean, it's possible that it's not possible. Yeah, we can't do that, but let's see what we can do. Now, remember, we discussed this the other day. Conjugates sometimes can be very helpful, especially with square roots. What are conjugates? Okay, conjugates are a pair of numbers. Actually, what I should say is not so much numbers, but binomial expressions, where the sign of the second term is different. Okay, what does that mean? For example, x plus 2 and x minus 2. Radical x plus 5, radical x minus 5, that kind of thing. 3x minus 7, 3x plus 7. Okay, so here's what we're going to do. We're going to take this expression and we're going to multiply both the numerator and the denominator by the conjugate of the numerator. Now, that strategy is guaranteed to simplify the numerator. We don't know what will happen to the denominator. Okay, so why don't we show why? All right, so let me copy this. So what I want to do is just focus on now the numerator can be expressed or calculated with FOIL. Because we have two binomial terms, meaning they both have two components in here. So F will be these two. Now, when I multiply these together, you can see that I've got radical x plus h squared, which is simply x plus h. Oh. Okay. O would be these two. I would be these two. And then last would be these two. And you can see these two will cancel each other out. So ultimately, you'll end up with x plus h plus x, 2x. Oh, wait a minute. Sorry, I missed the negative sign here. That doesn't help. That's better. All right, so it just reduces very nicely to just h. All right, now the denominator is pretty straightforward. All you're doing is multiplying all the two terms by h. All right, so we know that the numerator is just h. The denominator, we can rewrite this. Well, here we go. This is very convenient because these cancel each other out. Okay. So we didn't even have to multiply them across. Now, when we substitute 0 for h, we end up with radical x over radical x, 1 over 2 radical x, or you can think of this as 1/2 x to the minus 1/2 power. They both mean the same thing. Now, what's great about this is that you now have a formula. You can calculate the actual tangent line slope at any point on this function. Okay, so let's see. The original, oh yeah, it's just radical x. So in other words, which looks like this. So with that formula, whatever x is, I can find the derivative or the slope of the tangent line at that point with this function. Okay, I don't have to keep doing it for every individual point. I've got a formula that will work for every point on that function. Okay, good. Now let's do this example. Now we're going to use the same approach. So f of x is x squared minus 2x. So here's the definition that we're looking for. F of x plus h will therefore be x plus h squared. And then we have minus 2x. Okay, so in other words, the x has been replaced with x plus h in both terms. F of x itself is right here. So we expand this one, and if you use FOIL on it, you'll get x squared plus 2xh plus h squared. Here we distribute -2 over both of these terms with minus 2x, minus 2h. Then we drop the parentheses down here. We have minus x squared plus 2x. Now, luckily, some of those terms do cancel each other out. Otherwise, we really have a mess on our hands. Okay, so which ones drop out? Let's see, we got rid of these two. These two. So we're just left with 2xh plus h squared minus 2h. But remember, now we have this h in the denominator, so we have a lot of canceling here. we're left with very simply 2x plus h minus 2. And as h goes to 0, we just end up with, oops, pointed to the wrong thing. This just goes to 0, and we end up with 2x minus 2. And that, again, is the derivative of that function. We can find the tangent line slope at any point for any x. All right, now here's a discussion about the notation, which I've already mentioned to you. There's a few different ways, and these are not the only ones, but these are the most commonly used ones that you use to see for the derivative. By the way, it'll come up soon enough. I might as well mention it to you now. It's possible to take the derivative of a function multiple times. Now, you're going to ask, why would you do that? Well, there are good reasons why you might want to do something like that. So what I want you to see notation-wise is that this is what we're going to call the first derivative, or just the derivative. When you hear the word derivative, it means the first derivative. But if you reapply the derivative a second time, it becomes known as the second derivative. And you'd be surprised how useful this proves to be. Not so much the higher order ones, like the third derivative, you don't see that very often. But in applied fields, the first and second derivatives are the ones you'll use all the time. So for the second derivative, you can write it as f double prime of x, y double prime, or d squared y over dx squared. Now, why is that the case? Because what you're actually doing is this. So by convention, we write it as d squared y over dx squared. So we won't get to this for a while, but I just want to mention that this is how the notation would work for the second derivative, which simply means you're applying the derivative twice. Okay. Now, here's an important result. If f is a function that includes a in its domain, f of x is therefore differentiable, and it is continuous. So if a is in the domain of a function, we don't have to check for continuity. It's understood, or it's guaranteed, that it is differentiable at that point at least. Oh, here it is. Okay, I was afraid I was jumping the gun a little bit here. It's right here. Higher order differentiation. The rules may be applied to a function more than once to get higher order derivatives, like the second and the third and the fourth, etc. But you're not going to see the third very often in practice. These are the ones you'll see these quite often. The rest, very infrequently. Okay. And of course, they also have their own. You see now, suddenly it becomes f prime prime, f triple prime of x, y prime prime prime, or y triple prime, and d cubed y over dx cubed. All right, so with all that being said, we can now start to define actual rules. We don't want to have to use limits every single time. It could get so messy, it's really not worth the trouble. Instead, we have a series of rules that we can learn to help us with just about any situation that arises. And so we'll start with some basic cases. And you can see, well, there's quite a few of them. But you'll see they make perfect sense. And so we have the following 7 rules that we need to be very familiar with. The so-called constant rule, the power rule, the rule for sums and differences, the product rule, the quotient rule, the generalized power rule, and finally, the chain rule, which will really help us with very complex situations. All right, so we'll start with the easy ones, work our way up to the more complex ones. The constant rule couldn't be any simpler. The derivative of a constant is equal to 0, end of story. And you can see why, because the derivative represents a rate of change. A slope, I mean, the derivative is the slope of a tangent, but the slope itself is simply a rate of change. A constant doesn't change. Therefore, by definition, the derivative of any constant k is simply 0. All right, if only they were all that easy. All right, now this one is incredibly important to see this all the time. So in this example here, just bear in mind that K and N are both constants. X is the only variable in this expression. So the derivative of that f of x, let me repeat it up here, is n times k times x raised to the n minus 1 power. So what you're basically doing is moving the n becomes a coefficient, k doesn't change, and you subtract 1 from the exponent. So for example, for something like this is k, this is n. The rule tells me n k x to the n minus 1 is 7 times 5 times x to the 7 minus 1, which is 35 x to the 6th power. So in other words, again, all you've done is multiply the entire expression by what was the original exponent, and then you subtract 1 from the exponent. So we'll get a lot of practice with this one. This one will show, it shows up all the time. It's something we'll see quite regularly. All right, here's another quick example. Our function is 3x to the 4th. All right, so that's the rule. So if we start out with k x to the n, the first derivative is n k x to the n minus 1. So here k is 3, n is 4. So your derivative will be 4 times 3 times x to the 4 minus 1. Or we can simplify that as 12x cubed. All right. So how about this one? Now, it can get a little messy when our exponent isn't a positive integer, but the rule never changes. So let's look at another one. How about 6x to the minus 3? All right, so we can see that here's our k. Remember here, this is negative. So we're going to wind up with negative 3, 6, x to the minus 3 minus 1. So that's minus 18 x to the minus 4. So it's easy to make algebraic errors with something like this. We have to be careful. Now, I'm going to show you an interesting result. It turns out the constant rule is just a special case of the power rule. What do I mean by that? Okay, in other words, it doesn't need to be a separate constant rule, because, let's see why. Might as well be more formal, like capitalizing. Here's why. So imagine you have a number like this, 7. Well, implicitly, you could write this as 7 times x to the 0 power, because x to the 0 power is just 1. And so now you can apply the power rule where k is 7 and n is 0 rather. All right, so then if you apply the rule, look what's going to happen. 0 times 7 times x to the 0 minus 1. But the 0 here ensures that the entire term will just be 0. So there you go. So and yes, the constant rule is just a special case of the power rule. Okay. Now, what about the rules for sums and differences? This is as straightforward as it gets. All right. If you have a function which is a sum of two other functions, the derivative of that function is the sum of the individual derivatives. Okay, that's all there is to it. It's that straightforward. Okay, so f prime of x equals g prime of x plus h prime of x. And of course, as is so often the case, the same thing would be true for subtraction, meaning that if I'm subtracting, if it's g of x minus h of x, the derivative is simply g prime of x minus h prime of x, which should surprise nobody. Well, all right then. Let's look at a couple of examples of this. So here's a function. It's a sum of two other functions where we can think of this first term as g of x, and this one could be thought of as h of x. The rule tells us that f prime of x is g prime of x plus h prime of x. Now, I can apply the power rule to each of these separately. So for example, let's start with g of x. So this is our k and this is our n. G prime of x is going to be n k x to the n minus 1, 2 times 3 times x to the 2 minus 1, 6x to the 1, or 6x. H prime of x, h of x is x cubed. By the way, I just want to point out here, there's an implicit coefficient of 1 here. Okay, so in other words, you can think of this as 1 times x times 3, which means this is your k, this is your n. H prime of x is nkx to the n minus 1, 3 times 1 times x to the 3 minus 1, it's 3x squared. So the final result, f prime of x, is just 6x plus 3x squared. So basically, you're just doing the power rule twice and adding them up. All right. And, I guess we don't need a separate example for the to show what happens when we subtract them. the difference rule. But now the next one is going to be just a little bit more challenging. All right, so far so good. I mean, we've seen the constant rule, and we've seen the power rule, and we've seen the rule for sums and differences. Now we're going to get into the tricky territory. What about products? It would be nice if the derivative of a product is simply equal to the product of the derivatives, but unfortunately, it's not that simple. This is the first rule that is actually very complicated. And you really should memorize this. It's that important. So let me just show it to you. And so here's how it works. So again, we're assuming that f of x is the product of two other functions. The derivative is, think of this as the first function, and then this derivative of the second. And then we have the second function, and then we have the derivative of the first. So in other words, in both cases, you're taking one of the functions and multiplying it by the derivative of the other one. So you can see how the potential exists for these to get very, very messy. So if you're making up a list of things to memorize, I would definitely add this to the top of the list. Now I know that we're doing this online, so you don't have to sit down and take a test in the classroom, but just because you'll run into this so often, and because you may end up in Calc 2 as well, I would definitely memorize this. It's that important. In fact, I'll put big arrows here to remind you, yes, memorize this one. Within any discipline, there's always a handful of ideas that really you have to lock them up here. I would put this at the top of my list. Okay. Now some things are, like you'll see as we go along, some concepts prove to be more useful than others, but this is definitely way up there as far as importance goes. All right, now let's look at this. Now, by the way, sometimes you can avoid this by directly multiplying the two and simplifying it. It does happen sometimes. Like here's an example where you could have done it that way. Like if you notice, there's nothing to stop me from multiplying these out and then applying the power rule. And we'll do that to confirm this, but let's use the product rule first, just to get some practice with it. By the way, some books do change the order of this a little bit. You can see that there's multiple ways it could be written. But this is one of the standard ways. If you read another book, another source, you might find that the sequencing is slightly different, but it ultimately is the same thing. So anyway, so based on the power rule, we know that g of x is 3x squared, or that implies that we'll have 2, 3, x to the 2 minus 1, 6x. For h, h prime, we'll have 3 times 2 times x to the 3 minus 1, 6x squared. Now we apply the rule. All right, so it's down here in this slide. So remember, g of x is 3x squared. H of x was 2x cubed. G prime of x turned out to be 6x. H prime of x was 6x squared. So that's why it looks like this. Here's G of x, here's H prime of x, then we have H of x and G prime of x. Now we just use algebra. 18x to the fourth, 12x to the fourth, we end up with 30x to the fourth. Now, what if we had done this? We said, maybe this isn't necessary. If you multiply these out in the first place, you would have had 6x to the fifth, which is, and remember, think of this as kx to the n. F prime of x is nkx to the n minus 1, which in this case would be 5 times 6 times x to the 5 minus 1. And what do you know? It's just 30x to the 4th. So sometimes you can avoid using this rule if you simplify the expression before you get started. Okay, just be aware of that. But if not, well, then you go ahead and use the product rule. Yeah. Now, the quotient rule, if anything, is even messier than the product rule. You'd think it would be similar, but unfortunately, it's not quite that simple. The quotient rule is another rule you should memorize, just because it'll come in handy. It's like anything else. What do you memorize? You only memorize, memorize, for example, your social security number or your credit card number, whatever the case may be, because you never know when you might need it, and you don't have it written down somewhere. Having it memorized is a huge help. So the same thing happens here. There's certain things you just should have them memorized in case you need them. Anyway, so here's the quotient rule. So it's g of x over h of x. And of course, this applies as long as h of x is not 0. Oh, you're in for some bad news. Look at this mess. Oh, no. Yeah, ouch. Actually, I'll tell you what. No, no, no. I was hoping there might be a connection between the two. Not really. All right, you might as well just go ahead and memorize it. So you got h of x, g prime of x, minus g of x, h prime of x, all over h of x squared. Yes, I know it's a mess, but you can memorize that. All right. I'm going to copy this to the next slide so we don't have to keep scrolling back and forth. And, along the way, if you notice, I did mention way up front, the power rule, it's hard to imagine a more important rule. Because even if it doesn't start out as a power rule problem, often a lot of the individual components of a problem require it. So I'll just sneak this in here, just in case we need it. But after a while, I mean, it would be almost impossible not to have this one memorized because you're going to need it so often. All right, so yeah. Uh, All right, so there you go. Everything's already in place. Okay, this is everything you could possibly need to know for this next problem. So we've got this ratio. By the way, just like with the product rule, if you find a clever way to simplify this, then you may not need to use the quotient rule at all. Okay, you might get lucky. You might be able to reduce it to something simpler, but it doesn't look like that here, does it? No. So the numerator is g of x. The denominator is h of x. So you're going to apply the power rule for g of x 3 times. Well, actually, technically, this is the constant rule. So you're going to have, let's see, what you're actually doing is you're applying the power rule to each of the first 2 terms. So if you have 3x squared, again, just to get some practice, the derivative is nk x to the n minus 1. In this case, that would be 2, 3 x to the 2 minus 1, or simply 6x, because the exponent here is 1. For the minus x, I'm going to watch it here. That means that k is -1, n is 1. This one's a little tricky. So there's an implicit 1 here. So the derivative, of course, as always, is nk to the x to the n minus 1. We're going to have 1 times -1 times x to the 1 minus 1. -1. And then, of course, the derivative, if f of x is 1, based on the constant rule, this is just 0. So what that means is we now know that g prime of x is the sum of those 3 terms that we just created. Well, actually, let me just rewrite it, the whole thing. If g of x is 3x squared minus x plus 1, g prime of x, we just showed, is equal to 6x minus 1. H of x is 4x cubed minus 3x squared. So if we want to break these down and take each derivative separately, so the first term here has a derivative of 12x squared. And then for the negative 3x squared, negative 6x. So that means that altogether, h prime of x is 12x squared minus 6x. All right, so now we can apply all of this. Substitute this into the rule, that is. All right, so let me just quickly remind us that, oh, here they are. Let's just copy these into the next slide. Oh, all right. So now here's the rule. So I'm going to plug in. Here is our h of x, g prime of x, minus g of x, h prime of x, all over h squared, h of x squared. Now, you'll probably be able to consolidate the numerator. The denominator, maybe not so much. You can leave it like this, but usually we try to simplify it a little bit more than this. That is a bit of a mess. It may turn out that you can simplify it, but let's just see what we've got. Now, these can actually be solved with FOIL. This is 24x to the fourth, negative 4x cubed, negative 18x cubed, positive 3x squared. So this first expression is 24x to the fourth minus 22x cubed plus 3x squared. All right, now what about the second term? Oh, bad luck. This is not something we can do with FOIL. Oh my God. All right, so here's what you have to do. So you could write this with a 0 if you want to. We don't need it, but and then we multiply this one, 12x squared minus 12x cubed, and then finally 36x to the fourth That's the second term. Oh my God. I'm not sure if this was worth our while, by the way, but it's good practice, I suppose. Oh. So gathering up everything we just did. In the numerator, we'll have results of that FOIL, which was 24x to the fourth minus 22x squared cubed rather, and then plus 3x squared minus this mess, 36x to the fourth All right, let's just simplify the numerator and let it go with that. I think that's enough of a mess for one day. All right, so So it's 24x to the 4 minus 22x cubed plus 3x squared. Now I have to subtract that entire mess here. So it's negative 36x to the 4 plus 6x cubed minus 18x squared plus 6x, all divided by that same denominator, which is 4x cubed minus 3x squared squared. All right. So if you look at all the like terms, all right. Well, I was a bit overkill, I thought, but here we go. Now you can, you could expand the denominator and see if maybe you can simplify it. It looks like when you're done, you'll be able to reduce it by at least one factor of x, but I'm not sure how much trouble it's worth to do this. But this is what you have to do with the quotient rule. Now, what's coming up next is another one of the incredibly important rules. It's basically an extension of what we did earlier with the power rule, just the plain old power rule. If f of x is k x to the n, f prime of x is nk x to the n minus 1. So you can see the parallels with what we're doing now. This time, though, there can be a constant out here. We don't have to worry about it. If there is, it would just stay outside anyway. But the key is that instead of having x to the n, we have a function of x to the n. And now look what it does to our results. We have n g of x to the n minus 1, just like we had up here. But then all of a sudden, we have that wrinkle, that extra complication. And so this becomes known as the generalized power rule. We're going to save this for next time. But first, before we even do that, I'm going to go through a bunch of examples of applying the rules that we've learned so far, just because we need the practice. Okay. So that will be coming up next. A lot of practice with the rules we've done so far, and then we can get back to this generalized power rule. All right. So I'll see you next time.